standard deviation going to be? 16 over the square root of 25. Okay, so I take sample size 25, I put that in there. So 16 over the square root of 25 is going to be 3.2. Okay. So if I were to graph that comparatively, we would have the same mean at 100, but the standard deviation is now much more narrow, 3.2. So basically, let me just kind of zoom in on that one. I have a mean of 100. My standard deviation is 3.2. And I'm asking what percent of samples of size 25, or basically what's the probability that a sample of size 25 ends up with an average of 104 or more. So here I've got to get a z-score. 104 minus 100 divided by 3.2. What is that? 1.25. Okay, great. So 1.25. And so what is the probability that I am greater than 1.25? 0.1056. Okay. So if you look up 1.25 in the normal table, you get 0.8945. No, 444. 0.8944. But then I'm just using the symmetric property, so you can also look up negative 1.25, and the area to the left of negative 1.25 is going to be equal to the area to the right of positive 1.25. So here, the answer to this question, what's the probability that the average IQ of these 25 people is 104? The answer is 0.1056, or basically 10.5%. Is that good? Okay, so okay, so this works, and but again, all of these things you got to kind of at the heart of it, we do need to check the conditions, okay, or at least they should be in the back of our mind, okay. So if I didn't say I randomly sampled, okay, if I say I selected 25 students at UCLA, the answer is going to be different, okay? Because that's no longer a random sample. And actually, if I take a sample of 25 students from UCLA, I would not be able to answer this question because we have no idea what the sampling distribution looks like, okay? We only know the sampling distribution follows this thing when it's a random sample and when the sample size is large enough. Okay, and in this case, any size sample would have been large. Okay, is that all right? Here, why don't we we'll take a little break right now, and we'll come back in 10